Hi everyone! In the video today, I will explain some of my own research about geometric structures on surfaces generalizing the complex structure. This is called the higher complex structure. In order to understand this video, I recommend you to look at my other video about the puncture Hilbert scheme. This video is part of a masterclass given at the conference Topics at the Interface of Low-Dimensional Group Actions and Geometric Structures. Here we go. Let's start by thinking about what a geometric structure is. In order to get geometric structures on manifolds, there are two ways to proceed. Either you start by your manifold and then you add some object, you add something additional, or you change the very definition of your manifold. You change the space on which your manifold is locally modeled. If I consider, for example, the complex structure, this is of the second kind, because a complex structure on a manifold is a manifold whose charts are not open subsets of some Rn, but of C to the n. And then you demand the transition functions to be holomorphic. You could also define what is called an almost complex structure. In this case, you start from your manifold, and for each point, you add an operator which acts on the tangent space and whose squares minus the identity. And these operators have to vary smoothly with respect to the point. It appears that often in these two ways to define a geometric structure, there is a link. In the example just given, a complex structure always induces an almost complex structure. Because when you're modeled on C to the n, you know what it means to turn by 90 degrees. This is just the multiplication by I. And this operator, squared, gives minus the identity. Conversely, if your manifold is a surface, you can always get from an almost complex structure a complex structure. This is not true in general, where you need some integrability condition, while the abstraction is given by the Nienhuis tensor. Another big class of examples is given by Thurston's GX structures. I will not say anything about this, just for those who know about it, this is another example of the second kind, where you change your model space. Okay, so once you have a geometric structure, the study will always be in 3 steps. You will study the structure at one point, then locally, and then globally. Take, for example, the Riemannian structure. You know that for every point, it is possible to choose a local chart in which the scalar product just becomes the standard scalar product. On a local level, you know that there is some invariant given by the curvature. So in order to go to the global theory, you have to fix this curvature. For example, you fix it to be constantly -1. Then what you get is the moduli space of hyperbolic structures. If you take as example the complex structure, then the study at a point in the local study is trivial, because by definition a complex structure is changing the model space, which is already a local description. So the only interesting part of this geometric structure lies in the global theory, where you define a moduli space. In the case where your manifold is a surface, various different kinds of geometric structure gives miraculously the same moduli space, which is called Teichmüller space. You can see this Teichmüller space first as the moduli space of all complex structures. So you take the space of complex structures and you define on this an equivalence relation. Two complex structures are considered as the same when you can go from one to the other by an isotopy, meaning a diffeomorphism of your surface which is isotopic to the identity. As we have just seen, on a surface, a complex structure is the same thing as an almost complex structure. So Teichmüller space is also the moduli space of almost complex structures. Quite surprisingly, Teichmüller space is also the moduli space of all hyperbolic structures, where the equivalence relation is still taken by isotopies. And you can even consider it as a moduli space of all Riemannian structures when you quotient out by isotopies and what is called conformal equivalence. The two metrics are considered as conformally equivalent if you can write one as the product of the other by some strictly positive function. And finally, Teichmüller space can be described as a connected component of what is called the character variety, which is the space of representations of the fundamental group into the group PSL2R, mod out by global PSL2R action. Where does this character variety comes from? If you take a surface with a complex structure, then this complex structure will induce a complex structure on the universal cover. And by the uniformization theorem, if your surface is of hyperbolic type, your universal cover as complex manifold will be biholomorphic to the hyperbolic plane with its complex structure. And so the fundamental group acts on the universal cover by deck transformations, which are isometries. The isometry group of the hyperbolic plane is precisely PSL2 of R. This is the way to get a representation from a complex structure. Conversely, when you have a representation of your fundamental group, then you can quotient the upper half plane by the section, and you will get the surface with a complex structure. And this works when this action is faithful and discrete. And two such representations give the same structure, the same complex structure on the surface, if and only if they are globally conjugated by PSL2 of R. Teichmüller space admits a natural generalization, which is called the Hitchin component. In fact, in the various viewpoints we have just seen of the Teichmüller space, it is the last viewpoint which will be generalized. So the Hitchin component is a connected component of the character variety where you replace the PSL2 of R by PSLN of R, or more generally by some split real form of a complex semi-simple group. This component can be characterized as follows. You start from your fundamental group, you take a Fuchsian representation to PSL2 of R, so this is a representation which comes from Teichmüller space, and then there's a map which is called the principal map from PSL2 of R to PSLN of R, which corresponds to the unique irreducible representation of SL2 of dimension n. So if you take the compositions, all compositions of this kind, they will all lie in one component, which is Hitchin's component. So you can describe Hitchin's component as representations which can be continuously deformed into a composition of this kind. So Hitchin himself, in his paper of 92, described this component using Higgs bundle techniques. And in particular, he finds a parametrization of this component by holomorphic differentials. So the big open question is there a geometric way to define this Hitchin component? Meaning, can you describe it as a moduli space of some geometric structure on the surface? We have seen that Teichmüller space describes various geometric structures. But up to now, there's no geometric structure known whose moduli space would give the Hitchin component. In this talk, I will describe a new geometric structure we constructed together with Vladimir Fock, which we call the higher complex structure, because it is a generalization of the complex structure. This higher complex structure has various interesting properties, and conjecturally, its moduli space is exactly the Hitchin component. So this would precisely answer this open question. Before defining the higher complex structure, let's take a closer look on what the complex structure is. So I fixed some surface of genus at least 2, and we have already seen that the complex structure is the same as an almost complex structure. So we have some operator J whose square is the minus the identity. So this operator is an object of linear algebra. And to understand a matrix, what we usually try to do is to diagonalize it. For the operator J, its characteristic polynomial is given by j squared plus 1 equals 0. So the eigenvalues are given by plus and minus I. So in order to diagonalize it, we have to complexify the tangent bundle. So the operator J is in fact encoded in a splitting of the complexified tangent bundle into a holomorphic and an anti-holomorphic part, the 0, 1 and the 1, 0 part. In fact, these two directions are complex conjugated to each other. So it is sufficient, in fact, to knowing about the anti-holomorphic part, for example. So you can say that a complex structure is completely encoded in a given direction in each complexified tangent bundle. Because again, when I give you this direction, you can complex conjugate it. Now you have these two eigendirections, so you know your operator J. It is given by plus I on this space and minus I on this space. And once you have the operator J, you have the complex structure. You can integrate it. In more sophisticated language, you could say that the complex structure is a section of the projectivization of the complexified tangent bundle. The projectivization is pointwise. In fact, to be precise, we need one more condition, what you call the reality constraint. In fact, the direction I give you has to be different from its complex conjugate, because these two directions correspond to different eigenvalues. So this is the extra constraint you have to put. So now, in the first part of my masterclass, we have seen that the projectivization is the zero fiber of the two-point Hilbert scheme. So you remember two points in the plane describe generically a point in the two-point Hilbert scheme. And when these 2 points collide together, the Hilbert scheme will retain as extra information the direction from which the second particle came from. So now that we have described the complex structure in this form, it is easy to guess the generalization. But we have to change one thing. We will replace the tension bundle by the cotension bundle, because we will need the symplectic structure of the cotension bundle later on. So here we go for the definition of the higher complex structure. The higher complex structure is a section of the zero fiber of the n-point Hilbert scheme applied to the complexified cotension bundle. It is important to notice that you apply this fiber-wise. And we have one extra condition. We need that for every point, the direct sum of the ideal plus its conjugate is the maximal ideal supported at the origin. Notice that for n equals 2, we get precisely the complex structure. And this extra condition, I plus I bar is this maximal ideal, becomes exactly the reality constraint in the setting of the complex structure. In order to write down explicitly the higher complex structure, let's fix some coordinate system. So I take some reference complex structure on my surface, which is given by coordinates z and z bar, and I will denote by p bar the linear coordinates in the complexified cotension bundle. With this, I can write the higher complex structure for each point. It is given by some ideal, I, which depends on z and z bar, and it is of the following form. It has two generators, one which is nilpotent, p to the n, and the second one is p bar equals some polynomial n p, which is in fact this Lagrange interpolation polynomial, which we have seen in the last lecture. In fact, we have seen in the last lecture that a generic point of the zero fiber can be written in this form. But in fact, the condition that I plus I bar is this maximal ideal, which now we can write as the ideal generated by p and p bar, this condition assures that we are in the generic case. We are in the big chart of the Hilbert scheme. So at every point, we can write our ideal under this form. And the coefficients of this Lagrange interpolation polynomial, we call them higher Beltrami differentials. Because for n equals 2, there will be only one, the mu2, and this mu2 is in the literature known as the Beltrami differential. How can you think of this higher complex structure? What kind of picture you may have in mind when you work with them? Due to the various viewpoints we have seen on the punctual Hilbert scheme, you can also have various viewpoints on this higher complex structure. First of all, we have seen that the zero fiber can be thought of a jet of a curve at the origin. So we can imagine that we do this now at every point of your surface, so you get something like a hairy surface. But be careful, the hairs are polynomial curves in the complexified cotension bundle. We've also seen that the zero fiber is in fact given by the total punctual Hilbert scheme, where you imagine that your endpoints will all collapse together to the origin. So you can imagine that on your surface you start by an n-fold cover, so a choice of n distinct points at each fiber, and then you have to imagine that this n-fold cover collapses to the zero section. So in some sense, what the zero fiber retains as information is a jet of a complex surface along the zero section inside of the complexified cotension bundle. In the matrix viewpoint of the punctual Hilbert scheme, our definition of the higher complex structure gives the following. So at every point, we have given a pair of nilpotent commuting matrices. And since we have a section of the cotension space, in fact, these two matrices are part of a one form. So the higher complex structure can be seen as a matrix-valued one form, which we can write as phi1 dz plus phi2 dz bar, where phi1 and phi2 are nilpotent commuting matrices. So to be more precise, it is in fact a conjugacy class of these matrix-valued one forms. So now that we have our geometric structure, we also need an equivalence relation. An equivalence relation we want to put on these geometric structures in order to construct a finite dimensional moduli space. It turns out that the space of diffeomorphisms of your surface is not sufficiently large, because in some sense our structure lives in a neighborhood in the cotension bundle and not only on the surface. So the appropriate notion of the equivalence relation is the following. we call a higher diffeomorphism a diffeomorphism of the cotangent bundle, which is Hamiltonian, meaning generated by some function, which preserves the zero section setwise. So if you restrict the higher diffeomorphism on sigma on your surface, then you just see a usual diffeomorphism, which is in fact isotopic to the identity. But in the fibers, the higher diffeomorphism can act non-trivially. So in particular, it can be nonlinear in the fibers, and it can even mix up the fibers. So how do the higher diffeomorphisms act on the higher complex structure? Intuitively, when you see a higher complex structure as an n-fold cover which collapses to the zero section, you can say the following. The symplectomorphisms of the cotangent bundle, they will act on the space of n-fold coverings, because it's just an n-tuple of points over each fiber, and the section will admit a limit when this cover collapses to the zero section. To describe the section more precisely, let's take an ideal with two generators P and Q, and take some Hamiltonian function on your cotangent bundle, which generates a flow which generates the symplectomorphism. Then your ideal will change as follows. The first generator, P, its variation is given by the Poisson bracket of P with H. So this is a standard formula in symplectic geometry, which gives you the change of a function under some symplectomorphism generated by some function h. But in our case, we look at the variation of an ideal. So we have to take this Poisson bracket modulo the ideal. And the same equation is true for the second generator as well. Notice that from these formulas, we see that there's only a small part of the higher diffeomorphisms which act non-trivially. When you take a Hamiltonian H and you develop it in the Taylor expansion, then only the first n terms of this expansion will act. All the higher order terms will not contribute to a non-trivial action. So now that we have a geometric structure and an equivalence relation, we can look at the local theory. It turns out that any two higher complex structures are locally equivalent under higher diffeomorphisms, meaning that locally there's no invariant. This also says that the only interesting geometry of the higher complex structure lies in the global theory. So we define the moduli space of higher complex structures, which we denote by Tn hat, as the space of all higher complex structures modulo higher diffeomorphism. This moduli space has the following properties. First, it is a contractible manifold of complex dimension n square minus 1 times g minus 1. Second, there is a forgetful map going from Tn hat to Tn minus 1 hat. And in particular, you can go down until T2, which is just the usual Teichmüller space. So a higher complex structure induces a complex structure. We also have a copy of Teichmüller space inside the moduli space. Then we know that along this copy of Teichmüller space, we can describe explicitly the cotangent bundle, the cotangent space to our moduli space, which is given by this direct sum of holomorphic differentials. Holomorphic differentials of degree k, for k varying between 2 and n. And finally, we know that on our moduli space there is a mapping class group invariant complex structure. Maybe some remarks on how to prove this theorem. In order to prove this theorem, we use the higher Beltrami differentials, or to be more precise, the equivalence class of higher Beltrami differentials. In these terms, the forgetful map is just forgetting about the last Beltrami differential, μn. The copy of Teichmüller space are those Beltrami differentials for which all the higher Beltrami differentials are 0, and you just have the μ2. To compute the cotangent bundle, we use some variation argument, which is quite standard, and from this cotangent space, we can determine the dimension by using the formula of Riemann-Roch. Finally, the fact that our moduli space is contractible comes from the description as equivalence classes of higher Beltrami differentials. So when you see this theorem about our moduli space, and if you know some properties of the Hitchin component, you will see lots of similarities. This is why we have the main conjecture, which is that our moduli space should be canonically diffeomorphic to Hitchin component. So let's compare these two spaces more in detail. Both spaces, our moduli space and Hitchin component, are both contractible, and they both are of the same dimension. They have both an action of the mapping class group, but in the case of the Hitchin component, this is actually a quite hard theorem, which is due to François Laborie. In our case, it comes naturally from the fact that the higher complex structure is a geometric structure which is defined on the surface. Our moduli space has a natural complex structure, but for the Hitchin component, we don't know for the moment. On the other side, we know that Hitchin component, as a component of the character variety, has a natural symplectic structure. And in our case, we don't really see any symplectic structure. So if the conjecture is true, we would get at once a complex and a symplectic structure. So it would be interesting to see if both of these combine together to get a Kähler structure. For the Hitchin component, we know nothing about the cotangent bundle, because we only have a parametrization of this component. In our case, we have an explicit description of the total cotangent bundle. And finally, in our case, we have this forgetful map, where we don't really know about the fiber. For the Hitchin components, this forgetful map would be completely new, apart from the case n equals 3, where there is a description of the Hitchin component as convex projective structures. And so we know that there is a map from the Hitchin component of PSL3R to PSL2R, where the fiber is given by holomorphic cubic differentials. This is due to Loftin and Laborie. Let me explain to you how we want to tackle this conjecture, how to go from the moduli space of higher complex structures to the Hitchin component. So we know that the Hitchin component is a part of the character variety, which can also be seen as the space of flat connections. So what we need is to associate to a higher complex structure a flat connection. So first of all, we need a bundle in which this flat connection could live. It turns out that a higher complex structure always gives you for free a bundle on your surface. This is what I call the induced bundle. So this is a bundle of rank n, and the fiber over a point is just given by polynomials in P and P bar divided out by the ideal. So the ideal which is prescribed by the higher complex structure. We have seen that in the matrix viewpoint, the higher complex structure is given by a matrix valued 1 form. And in fact, this matrix valued 1 form, which we can write phi1 dz plus phi2 dz bar, lives in this bundle. And finally, inside this bundle of rank m, there is a canonical line subbundle, which is given by the common kernel of phi1 and phi2. So the idea is to start from this bundle and from this matrix valued 1 form and to deform it into a flat connection. Let me give you the big picture of how to get a flat connection out of the higher complex structure. In fact, we try to imitate, to some extent, the original approach of Hitchin. Hitchin's argument goes as follows. You equip your surface with a fixed complex structure, and then you consider what is called the moduli space of Higgs bundles. I will not explain what it is, but the main feature of this space is that it is hyperkähler. This roughly means that you have a one-parameter family of Kähler structures. So this one parameter, in fact, lives not in C, but in CP1. So you can draw the following picture. You draw a sphere, a CP1, and at each point, you write the complex manifold you see. So all the spaces you will write are the same topological spaces, but they might be different, seen as complex manifolds. In the case of the moduli space of Higgs bundles, you see this moduli space at one point of the sphere. On the opposite point, you will see the moduli space of Higgs bundles for sigma equipped with the conjugated complex structure. And for all other points, you see the character variety for the complex group, PSLN of C. The important feature is that you can go from any point to any other point in a canonical way. So you can associate to any point of the moduli space of Higgs bundles canonically a flat connection. This is called the non-abelian Hodge correspondence. And then Hitchin considers a map from the moduli space of Higgs bundles to the space of holomorphic differentials. So this is actually a space we have already seen as the cotangent bundle to our moduli space. And he constructs a section of this map, and he shows that through the non-abelian Hodge correspondence, the image of the section is a flat connection which has real monodromy in PSLN of R. This is the way he parametrizes the Hitchin component by holomorphic differentials. In our case, we start with the smooth surface, and the role of the moduli space of Higgs bundles is played by the total cotangent bundle to our moduli space. This should have a hyperkähler structure, and the picture should look quite the same as before. So at some point you see this cotangent bundle, at the opposite point you see some conjugated structure, and for all other points we should see the complex character variety. As before, there should be an analog to the non-abelian Hodge correspondence, meaning that to any point in this cotangent bundle you can canonically associate a flat connection in the complex group. And then in our case, we have the projection map of the cotangent bundle to our moduli space, and we can see our moduli space as the zero section of the cotangent bundle. So then we can associate to a point of our moduli space a flat connection, and its monodromy should be real. It should be in PSLNR. So the picture I just described is conjectural. What do we know for the moment? So we have a description of the character variety for the complex group as a space of some lambda connections of a specific kind, such that when lambda goes to 0, we recover the total cotangent bundle of our moduli space. The main missing part is to prove the analog of the non-abelian Hodge correspondence. So this canonical way to go from any point to any other point in this picture. If we admit that this correspondence exists, then I can show that our moduli space is canonically diffeomorphic to Hitchin's component. So in particular, I can prove that the monodromy of a flat connection which comes from the zero section is indeed in PSLN of R. Independently of the question whether our moduli space is the same as Hitchin component, it is possible to do lots of things with the higher complex structure. I will just pick two aspects which fits quite well in the spirit of this conference on group actions. The first aspect is about a higher mapping class group. We have seen that on higher complex structures there is an action by higher diffeomorphisms, which are Hamiltonian diffeomorphisms of the cotangent bundle preserving the zero section. But in fact, any symplectomorphism of the cotangent bundle which preserves the zero section will act on the space of higher complex structures. So we can consider two groups, the group of higher diffeomorphisms and the group of symplectomorphisms of the cotangent bundle preserving the zero section. So using some work of Ono and Banyaga, we can show that the group of higher diffeomorphisms is in fact the identity component in the space of symplectomorphisms preserving the zero section. This implies that when you take the quotient, you will get a discrete group. Furthermore, when you look just on your surface, which is preserved by all these groups, you will see the space of all diffeomorphisms quotiented out by the isotopies. So you get the mapping class group. And conversely, any diffeomorphism of the surface can be linearly extended to a symplectomorphism of the cotangent bundle. So we have a copy of the mapping class group inside of this quotient. But the question is this quotient strictly bigger than the mapping class group? If this was true, we could call this group higher mapping class group. Notice that the correct analog of the Riemann moduli space, which is Teichmüller space divided by the mapping class group, should be the moduli space of higher complex structures divided by higher mapping class group. Second aspect is some GL2R action. When you look at the case where n equals 2, our moduli space just becomes Teichmüller space, and the cotangent bundle of Teichmüller space has a description as the space of all half translation surfaces. So we know that this cotangent space is given by holomorphic quadratic differentials, and for every holomorphic quadratic differential, you can associate charts given by the integral from some base point to z when you take the square root of t. And these charts, they glue together either by translations or by a composition of a translation by minus the identity. This is precisely what a half translation surface is. You can go the other way around in constructing a half translation surface from a polygon where you identify several parallel sides together, so either by identity or minus the identity, and on the space of such polygons, there's a natural action of GL2 of R. This action is studied a lot in the context of billiards. It turns out that for any n, there is an action of GL2R on the cotangent bundle of our Moduli space. This action goes as follows. So a point in this cotangent bundle is in fact given by the total punctual Hilbert scheme. So you have two generators, one which is a polynomial in X, and one which is given by this Lagrange interpolation polynomial. And then you have to notice that you can write GL2 of R in a complex way. So you can write it as a complex matrix with entries A, B, B bar, and A bar. And such a matrix induces a change of the coordinates x and y, given by x prime equals ax plus b bar y bar, and y prime equals b bar x bar plus ay. So once you have this transformation of x and y, this induces a change of the t and the mu coordinates. And you can show that this is equivariant with respect to the action of higher diffeomorphisms. So in this way, you show that there's an action of GL2R on this cotangent bundle. So the interesting question now is how to use this GL2R action in a similar way as it is done in the theory of billiards. Thanks for watching this video. I hope you enjoyed it. You can ask your questions in comments. See you soon!